Okay, so in this video, we'll be looking at a way of writing really big numbers or really small numbers, and these appear in a lot of scientific study, because in different parts of science, we often do come across huge numbers or tiny numbers. Like, for example, the mass of Earth is about 6 trillion kilos, so we're thinking, is there a nice, clean way to write that without putting like 24 zeros or something every time we want to talk about it? Okay, we'll also be using the language of significant figures from last time. So here, we're trying to write this measurement of 696342 in scientific notation, but rounded to 3 significant figures. Okay, so what does that all mean? So here's our number. Everything here is, of course, significant. We have no random zeros at the end or anything. Okay, so if we want to only take 3 significant figures, we grab the first 3 digits of this measurement here, the 6, the 9, and the 6. Then because the next digit is a 3, we will round down to just a 696, as we normally would. Now I've left a little gap there, and that's because the convention here is to always put a decimal point after the very first digit. So right here. Okay, I'll explain why soon. But notice I've followed suit on the left-hand side. I've put that yellow decimal point there between the 6 and the 9 to match what we've got on the right, okay? And that's because we now need to fix the number on the right. See, we've made it 6.96, but the real measurement we're describing here is 696,000 or something, so we need to fix that decimal problem. And we do this by moving that yellow decimal point to its correct place, which for a whole number like this is all the way to the very end, the far right of the number. Now, to move a decimal point to the right is the same as multiplying by 10. Okay, and all we need to know now is how many times we need to multiply by 10. So we're going to keep a count, keep track of how many times we're pushing that decimal point across. Now remember, when we repeat a multiplication like this, that turns into a power. So keep an eye out also for the power of 10 increasing as we keep moving the decimal place up. So here we go. If we move it one place to the right, we've multiplied by, well, 1 copy of 10. Okay, then we move it again, so now it's 10 square. Okay, we move it again, so it's 10 cube. Then again, giving 10 to the 4. Okay, then one last time, giving 10 to the 5, and the yellow decimal point on the left is now in its correct spot, so we're done. Okay, we can put the kilometers there, and the number 6.96 times 10 to the 5 is now written in what we call scientific notation. So what's nice about this, apart from having a concise way to write huge or tiny numbers? Well, a good thing is we can easily see the significant digits in the number. Okay, the way it's set up, every digit on the left here in blue is always significant. Even if there are zeros, because they'd appear after the decimal point, they would still be significant, like in the last example of the previous video. Then this times 10 to the something part, the red part here, is purely to tell you how big or small the number is. Okay, it's a bit like the insignificant part, if you will. Okay, it just tells you the size of the number, okay, which is important, but not really related to the accuracy of the actual measurement, as we discussed in the previous video. So now I want to show you how this helps to solve the awkwardness of a number, like 26 million from last time. Remember, we wanted to say communicate, all right, that with the current population of Australia, actually 2 of these zeros are accurate. Okay, the number is precise up to there, and it's only after that point that we've done some rounding. Okay, and it was impossible to communicate this with just a bunch of zeros. Okay, a reader would not know how precise this number is. But if we put this into scientific notation, all right, with the decimal point there, then these 2 zeros at the end are significant for sure, and there would be no confusion whatsoever for the reader. Okay, Then, like before, we fix this number by moving the decimal point to the right. Okay, so we move it 1, 2, 3, 4, 5, 6, 7 times, okay? Meaning we times by 10 to the 7. And that's a good way to, again, communicate the accuracy of such a number. Okay, let's finish by giving an example of a small number, so say 0.000249, and we want it to two significant figures. Okay, remember the zeros at the start here aren't significant, they just tell you it's a small number. So when we grab our two significant figures, we go for the 2 and the 4 here. Okay, except the next digit is 6, which means we need to round up to 25 rather than just 24. We put in the decimal point, always after the first digit we grabbed, okay? And we need to now fix the number by multiplying by an appropriate power of 10. But notice this time on the left, we need to move that yellow decimal point to the left rather than to the right. And to do this, we need to multiply backwards. Okay, and so that means we need to multiply by a negative power of 10. Alright, so here we go. Backwards one step is 10 to the negative 1. Then negative 2, negative 3, negative 4, and we're done. So our number is 2.5 times 10 to the negative 4. Okay, and the takeaway here being that negative powers move the decimal point to the left, which lets us handle these tiny 0.000 something numbers. Okay, so look, this might feel weird and almost unnecessary for numbers that aren't really all that extreme like the examples we're giving you here and the things you'll be doing by hand. But again, in practice, if I'm dealing with something like the mass of the Earth, which is super important for exploring things like gravity and such, I would rather write something like this than something like that. Okay, especially if I have to repeat that string of zeros. Okay, so that's scientific notation. Thanks for watching. See you around.